Hi class, how are you doing everybody? We are on chapter 4 of 4.2. We are going to getting there for optimization question which will come in 4.3. You will see that that is the highlight of calculus. So that's what I tried to prepare you for. And 4.3 later on we're gonna see optimization and modeling. It uses a lot in reality of the engineering, science and math and finance and a lot of field in higher level. So I want you to continue study on 4.2 and so that you get to see 4.3 play well with me. So first, I want to talk about appetizer. There is a shape of the base, look like that, kind of curved in. And then I'm going to pour the water in the flour base. I want to find the graph between time versus the height it goes in. Before I'm going to graph this one, I want you to think about what if the shape of the base is just a uniform cylinder versus if it's shaped like cone shape. So then why I want to talk about these two, because when I pour in the water, let's say that like 1 minute it comes into like a 1 liter something, then think about carefully if it was uniform, then each time I'm gonna graph this one a little bit better for you. So each time it's gonna be filled in exactly same height because my shape of the base is uniform. So each minute or each 10 seconds, if it's gonna be filled in this amount same time. So I just gonna make example. Each minute takes about exactly same amount of the volume. Then if my base shape is a cone shape, it will be still each minute. It's gonna be same like this way, yes or no? Definitely not. You have to, that's the part that I want to think about. So if it's a cone shape, it's not gonna be fit in this way. First, probably this amount is going to be same as that amount, and then fill it. Do you see that each volume is going to be the same? This volume is the same as this volume is the same as that volume. So it's not gonna have the same height at all because each minute is gonna fit in as a volume is the same. So this volume has to be same as this volume has to be same as this because the rate of water pouring in each minute will be the same. So if it's like this, so let's talk about this one. If the base shape is this, then how I will just use this function. Then how is it gonna start? If I pouring in, very beginning is 0, and then each time it's gonna increase linearly, right? Increase linearly. So when it's top here, it's full. How about this one? If I want to graph this one, starting from 0, then first it's gonna go really fast, slower. So you see that each minute, when it's a time like this, first it goes really high, and then a little bit less. Do you see that? Because my height is changing each time, smaller and smaller, but amount of the time it takes to filling this amount is 1 minute or 1 second or 10 seconds, whatever you want to call. So do you see that my height is going to be increased a little bit slower if you see it this way? Do you feel it, class? So now if the shape is this way, how would that be? Then starting from 0, and as you see, let's say that each minute it can fill in this amount. Then whenever it gets narrower, do you see that it will be probably like that amount and then get smaller? But however, do you see that each volume has to be the same? These are all the same amount of the volume. Which means if you pour in the cup, they are all same amount. So measure the height here. So each time it was here, next time it was little bit higher, and then this time definitely higher, right? And then 4 seconds higher and slower and filled up. So 1 2 3 4 5 6 7, let's say 1 2 3 4 5 6, like 6 seconds while we're watching. Do you see that my shape of the graph is gonna go like this and then filled up? Does it make sense to you? Or you can also see as a rate of a change. Here it's gonna take slower because it's wider to fill in as a high, so it's gonna rate of a change is going to be slower. And then once you go on to middle part, it's gonna increase as faster. And then now back to slower. So do you feel that how the water will fill in is gonna have a shape, continuous function this way? Now your turn. So I want you to pause the video and I want you to try in-class activities. There's in-class activity 1, sorry, this is in-class activity 0, and then there's in-class activity 2, which we already saw in 4.1. So I want to pause it about 10 minutes and then do 1, 2, 3 and compare with me. Okay class, let's look at the in-class activity 0. So when you look at this, did you notice that I just basically tried to find the volume same amount and divide into 1, 2, 3, 4, 5, 6, 7, 8 seconds. So after that, I just draw the height of the each time. That's all I did. And I see the beginning part is gonna increase. Your height is going to be increased faster and then slower. So here it's gonna look like a curved function like this. And then after from here, you see this uniform shape that is going to be increased linearly up to when it becomes full. Okay. So that's how you can find it. Now in class activities, how did you do? So did you find critical point? I took the first derivative and then I found equal to 0. So I can have a 4 or 2 as a critical point. What does critical point mean? It can be 0 or undefined. So critical points are 4 and 2. But now we have to see that which one is local maximum minimum. You have to show me. You cannot just put it in without any evidence. What I need to see is, of course on the test, if I'm showing something like this, you have to graph it and then at 2. So I graphed this function, x-intercept 4 and 2. So x-intercept 4 and 2. And I graph as a stretch by 3. So stretch by 3. So here's my vertex. Then at 2, look at, this is my first derivative graph. Then my original function at 0, at 2, does it say the local maximum or minimum? This will be a local maximum because here says my original function increasing, original function decreasing. So it has to be increasing and decreasing. That is a local maximum. So at 2, that is a local max. And I plugged in 2 into my original function. Then I got 12. And this one, when you look at this, can you say that this represents local minimum by first derivative test? Because here's a decreasing, increasing, decreasing, increasing. And then F4 is going to be local minimum. So I plug in 4 and I got 8. So before pre-cal, do you think you can graph this one? Think about it. Without the graph calculator, we couldn't graph this one. But now using calculus, we have a local maximum at 2, 12. 2, 12, 5, 10, 12, and then local minimum at 4, 8, so about here. And then I also took another derivative, second derivative show me inflection point. I set equal to 0, then x is equal to 3. So inflection point is going to be 310. I plug into calculator, so inflection point. So I can roughly graph this one. Here says concave down and then touch the local maximum, and here's going to be inflection point and then concavity changes. So I can guess this graph will look like this way, right? If I make it even better, your y-intercept is negative a, so you can just drop it really sharp like this way past this negative a. So that's how we graph it, the function that we cannot factor, right? This one doesn't really factor nicely, so we graph it, and that's how you find. But careful how you find maximum minimum. You have to show me the evidence. This one has to be maximum, this one has to be local minimum by our first derivative test. Okay, let's do one more and then check with me. Okay, getting better class, in class activities 2. So I took the first derivative and then that's what I got. So I set equal to 0, and from here I will have only one critical point, which is going to be 1 over 2. Why? We saw this one previous chapter section. E to the negative 2e never gonna touch the 0 because your function is gonna look like this way. So only way that you can make 0 is this has to be 0, so only one critical point. Then how do I know that this is going to be maximum minimum? Look at this. This number is always a positive. So can I graph this one? 1 minus 2t, y is equal to. So if you graph it, 1 as a y-intercept, slope, negative 2t, and this is 1 over 2. So my first derivative graph shows that this is increasing, decreasing, increasing, decreasing at 1 over 2. That's where the point is increasing and decreasing. Therefore, I'm going to have only local maximum. I do not have a minimum at all. So I plugged in 1 over 2. Then into original function, I got 1 over 2e. Keep checking. And then that gives you 1.184. Then I took the another derivative, which is to find the inflection point. So I took second derivative, and then look at, I pulled out only positive number. You see that, Young, can I pull out -2? You could, but I want to keep it positive. This one is a positive so that I can compare this one as a regular function. Okay, if you put it negative, then it's going to be upside down with this one that you cannot see which one is going to be right answer. So keep it positive, positive. So I didn't pull out negative, actually I put it inside of negative, that's why negative plus, then that becomes as pulled out after -1. To organize, and I said equal to 0 from here. Do you see that t has to be 1? That is going to be my inflection point. So I plug in 1 to original function, then I get 1 over e squared. Because I get e to the -2, right? So I punch into calculator, then it shows that my inflection point is 0.135. So what does it say? From 1, now my graph, if I graph 2t minus 2, that's going to be, my graph shape is going to be this way. Okay, this way, right? 2t minus 2, that's -2, slope 2, and then this is going to pass through 1. Everybody agree? Then this is second derivative. This is a second derivative. So from 1, it's going to be saying that concave up or down, concave up. So up to 1, I have my inflection point, which is 0.135, and the maximum point 0.184. So concave down, right? And then careful, the rest of it is going to be concave up. But I do not have a local maximum, local minimum, so you just have to make it nicely continue. And I'm show this one already 3 times. Why? This is, as I have mentioned, it's very related to a lot of the pharmacy medicines or other things that we talked about, drinking coffee. So when it's going to be the peak time after you take the pill, you can see that half an hour later, you're gonna hit the peak time, and then you can calculate later on how often do you have to take the pill. Every 6 hours, every 12 hours, every 24 hours. That's how those people decide by looking at the graph. So earlier of the 4.1, if you look at, also there were example by 1 hour will be the peak, and then just try to feel that this graph is very important in chemistry and biology and those people who is gonna be in science. Okay. Okay, class, let's look at main dish of the 4.2. So we have some heavy ones that we are going to take a derivative, but before we do that, let's talk about what extreme value theorem means. Extreme value means basically local maximum, local minimum, global maximum, and global minimum. Those we call as extreme value. Just the word the biggest, because whenever you are going to have a company, think about you want to make the best profit with using the least amount of the material, right? So those what we are doing, and then we call as optimization. So remember that word, because I listen a lot on the news. Sometimes they always say optimizing this, optimizing the profit, optimizing the area, and that's what it is. So when you look at here, extreme value theorem means it's a little bit abstract, but as you see, always has to be continuous on closed interval. That means a closed circle. Then F has a global maximum value and global minimum value in closed interval. Remember, it has to be closed. So if my graph looks this one, then I must have global maximum and global minimum. Is that true, right? But what if it was open? Then how do we say that this number we don't know exactly, right? So those cases we could say undefined. Therefore, to have extreme values, you must have closed interval, okay, closed circle from A to B. Then you must have global maximum and global minimum. I'm not talking about local max, local minimum. You will have a maximum and minimum no matter what. So when you look at this graph, do we have a global maximum? Yes or no? No. Why is that? Because do we have a closed interval? No, it's not, right? And do we have a local? Yeah, we have a local minimum, but this is also, this case, a global minimum, right? If it's a smallest, let's look at next one. When you look at this one, can you say this one is a local minimum? This one is a local maximum. And this one is a local minimum. This one is also local minimum. However, can this be also global minimum, right? Because the smallest out of the whole graph Can this be global minimum? No, it's obviously not. This is a small list. And then do we have a global maximum? No, we don't, because there's also not closed interval. That's why. If it's closed, then it will be. If it's not, then not always will be. So careful about when we say that the extreme value exists or not. So let's observe this. Let's look at main dish question together. Okay, class, let's study our main dish of 4.2. Now we are going to graph the function and then observe the local maximum minimum. Okay, class, do you remember how do we graph this one before when you were in pre-calc class? If I briefly explain, you are going to find the domain and then it's going to have asymptote at 0 and 1. Do you see it? Horizontal asymptote and vertical asymptote and horizontal asymptote at 0 by taking long divisions and then taking xy intercept by plugging numbers. So you will get the xy intercept, plug in x as 0 if I plug in undefined. So there's no x intercept, there's no y intercept, not much information given. Anyway, so we use the xy horizontal asymptote and x-intercept, y-intercept in order to graph it, and then by plugging, and then we test it, and then that's how we graph. But this time, I'm going to show you how we're going to graph this one using calculus. So first of all, I'm going to find critical points. That means I'm going to take a derivative which makes undefined or equal to 0. So let's take a derivative. I can rewrite this function as 1 over x square minus x as my function. It's going to be easier to use power function way, polynomial way. So from here, if I take a product quotient rule, then denominator square, and now I'm going to take a derivative of the top, that's 0, times whatever bottom, minus, leave it, and take a derivative of bottom. Okay, everybody following okay? So when you do simplify, it cancels out as 0 times, and then I will have negative 2x plus 1 over x squared minus x squared. I want to keep it this way. Okay, that's my first derivative. Then let's set this one equal to 0. So do you see that denominator never gonna be 0 because of something square, or when it's going to critical point? What are the critical point here? I see the critical point two kinds. 1 over 1 makes 0, that is going to be 1 over 2. That's x. And then do you see another thing that makes undefined? 1 makes undefined. When x denominator is 0, that's undefined. So we have a critical point, right? And then we have to see that this one is not gonna be local maximum or minimum, because local maximum minimum happens that when it's equal to 0. This one is undefined, that it's not gonna help me for this one. But is it part of the critical point? Yes. But is it part of the local maximum minimum? No. Okay. Why? Because whatever makes equal to 0, that is only this value. So you need to show me that it's a 1 over 2. Is this going to be local max or minimum? How do we verify? Remember, now denominator is always positive, so I can graph this one. Y is equal to negative 2x plus 1. If I graph it, 1 and then negative 2x like this, what is this point? That is going to be 1 over 2. So from the first derivative graph at 1 over 2, is this critical point represents local maximum or minimum, class? That's going to be local maximum. Do you see why? Increasing and decreasing, right? Increasing, decreasing of your original function. So that's going to be local maximum. Then if I plug in 1 over 2 quickly, what do I get? It's going to be 1 over 2. 1 over 2 minus 1 is going to be 1 over negative 1 over 4. So I get negative 1 over 4. I got local maximum and half and negative 1 over 4. Then, what about local minimum? Do I have a local minimum? Do not exist. Why? Because I already know that that was a local maximum. I know that this is already undefined. Why did I put critical point means two meanings, equal to 0, undefined. So that do not exist. Then, I can find inflection point. How are we gonna find inflection point? We're gonna take another derivative. So let's take second derivative. Then one more time, denominator square. That's going to be fourth power. And then careful, I'm going to take a derivative of this one will be negative 2 times the number denominator, leave it, minus, and then leave it, and then take a derivative of this one. We have to use the chain rule, 2 times x squared minus x, and then there's going to be times 2x minus 1. Times 2x minus 1. Okay. I wonder if it's really necessary. Okay. I want to see that what makes the top 0. So I can pull it out everything. Do you see common factor this? And then I can pull it out common factor this. Oh, let's just pull it out without the negative. Then I maybe see something. So common factor 2 times x squared minus x squared, and then parentheses negative 1. Oh, negative. If I put this one in here, that's going to be plus, and then 2x minus 1 squared. So I try to find my second derivative and keep following my math here. So I found here, here, and then here, organize it, and then my second derivative turned out to be this. Please follow the work and see. So I set equal to 0. So is there any value makes 0 here? No. So therefore I get no inflection point. Then how I got my graph? I saw that from here local maximum 1 and negative 1/4. So I just graph it 1/2 and negative 1/4. And my graph says that left side is increasing, right side is decreasing. So I made it increasing and decreasing. And rest of them, what I did, I plug in my limit. When limit goes to infinity, 1/infinity means 0. So whenever it goes to close to x goes to infinity, it's gonna go close to your x-axis. And I plug in negative infinity, same thing is gonna happen. And then if I plug in x's limit 0, then it's going to be 1/0. It becomes a very big number, so you can put it here. And the other side, you can use a symmetric. So that's how I guess my graph using the calculus. Okay, there's one more question, and then I want to try in class activities and compare. Okay, let's look at in class activity 3. So from this function, I took the first derivative and then second derivative. So look carefully. First derivative, I want to find critical point. So set equal to 0. So I get 0 or 6. So look at, if I graph this one, do you see that it's going to be upside down quadratic, minus r squared. So it's going to be concave down quadratic, passing through 0 and 6, passing through 0 and 6. So without this one, we could roughly graph it with using our pre-cal. It's going to be 0 as x-intercept, y as x-intercept. It touches and then crosses. So do you see that I graph this one? Also, it becomes a negative x cubed graph like that, or a negative r cubed graph. That's why upside down. So first derivative graph shows that upside down graph. Then what can you say about this as 0? This one will be decreasing, increasing, so it has to be local minimum. And then as 6, if you look at, that's going to be increasing, decreasing, so that's going to be local maximum. So I put local maximum 6, local minimum 0. And how do I check? By my first derivative graph. And I plug in 6 into original function as a maximum value and then 0 as a minimum value. So everybody okay, find the maximum, minimum, and how you prove it to me that that has to be local max or minimum looking at the graph. Always make sure make it positive. And then second derivative graph, I just kept this one and then I took the derivative of my polynomial so that I don't need to use the product rule. So I just took the derivative directly. That's 18 minus 6r. So factor out by 6. Then what makes 0? I see that it makes 3, 0. So my inflection point will be at r radius as a 3. So if I plug into original, I get 3.54 as my original inflection point. So if I have a rough graph, now I can graph mine exactly how it look. 6, 10.6, 10.8, 5, 10, 10.8. That's my local maximum. Inflection point is gonna happen at 3, 5.4. So I can graph mine now even better. So why we do this? Before we learn this graph, you can actually graph rough shape, but in order to find maximum, minimum, we couldn't even find it without calculus 1. So we could guess it, but we cannot find the maximum value without graph. But now you can find those extreme values. You can find those extreme values. Okay, so I hope that was a summary, and then rest of them will be heavier and then more fun. So keep playing with me. Almost there. Okay, class. So today our today's highlight. We are going to find the maximum and minimum value of a given function. And this will be half 50% of this section 4.3. So I want you to understand your 50%. So when you do 4.3, it doesn't get too difficult for you. So let's do derivative of a given function. So local maximum, minimum means I have to find the critical point and then try to compute that what maximum, minimum is. So let's take a derivative. It's not easy, right? I will do one by one. You will get to do it several times. So just do together with me. Let's take a derivative. So you see this will be, it's a 1 over 6, right? Plus, now can you see as I can pull out 1 over 4? And then I want you to see that there will be chain rule in here. So 1 over 6, and then 1 over 5 fully front. And now taking derivative of the outside, that's going to be 1 over 2. And copy down 5 minus x squared plus 9. Do you guys remember? And take a derivative inside. I see another chain rule. Take a derivative over inside. That's going to be 2 times 5 minus x. 2 comes down and leave it, and take a derivative is a 0, and then times another inside negative 1. Are you following? Okay. Alright. So I took the derivative carefully. So organize. I have 1 over 6 plus, do you see I can cancel out this one, and then negative will make, I will just put as a negative 5 minus x over 4 over 5 minus x squared plus 9. Okay, let's see. Hope that is correct. So from here, I want to find critical point, so I'm going to set equal to 0. That means, do you see that I can move this one to right side, and then I can do cross multiplication. So I set equal to 0. I hope that I have enough room, or I may not. Then 1 over 6 is equal to, if I move this one, it becomes a 5 minus x over 4 root and 5 minus x squared plus 9. Okay, let's do cross multiplication. That will be 4 square root of 5 minus x squared plus 9 is equal to 6 times 5 minus x. Okay. Next one, I'm going to reduce this one, so it becomes a 2 and becomes a 3, and reduce it, and then I'm going to square, then it becomes 4, and that comes out equal to 9 and 5 minus x squared. Everybody okay? So I need to solve for this one. Then do you see that I have a 4 times 5 minus x squared, 9 times 5 minus x squared. If I bring right term to other side, you see that that makes a 5 times 5 minus x squared. And then other side is going to be 4 times 9, 45. 36. Okay, so solve for x. Divide by 5. 36 divided by 5. 5 minus x squared. I wish I had more room. And then square root is 6 over root 5 plus minus, and I get 5 minus x. Then I'm gonna bring x to that side, bring this one to other side, so x is equal to 5 minus plus 6 over root 5. And if we rationalize it, it's going to be 5 plus minus 5 over 6 root 5. Okay. So I found those are two critical numbers. So let's punch into calculator what that number means. Okay, class, so I hope that you got this one, and then I punch into this one into the calculator, which I got about 2.3116. And then I also put, that's negative part, and then if you put the positive part, I get 7.683. But do you guys remember extraneous solution? This case, if you plug in this one, it doesn't satisfy my equation. So when you look at this one, if I plug in 7.68, that's more look like answer, but it doesn't work because you look at here, 5 minus 7.6 is a negative, but here it says a positive. So this one is an extraneous solution. By plug in, that your solution will be 2.316. How do I know that that is a correct answer? Because remember, what does that mean? We have to find the extreme values. So it's going to be either local maximum or local minimum. And this one will be, now let me look at, this will be local minimum at 2.316, and then I have to explain the reason why local minimum on next section, so just wait for me. And then let me check with the decimals. So I punch this one into decimals and look at. So if you look at my decimals, I punch in same equation. I know it's hard to see my equation, sorry, I cannot really show it well, but that's the graph I received. And then I'm going to look at that point. Do you see the exactly same 2.317? Can you guys read it? Here's the 2.317, and when you plug in that number into original function, that will give me about 1.3. So now if you plug in this number, and that's going to be you have to plug in here, right? Original one, and then to 1.392 as a local minimum value. Okay, so this was a kind of a big rich derivative, and I want you to try one more. There's a class activities 4, and then now make it yours and look at my work. It will take up a whole one page, and take the extra paper so that you can work on a little bit better. Okay, class, let's look at in-class activities. How did it go? And if you do several times, it will get better. So when you look at this, just do algebra very carefully. And I got 1 by 1 as 4 minus plus root 3. So I have plus minus root 3. And then when you take here, you take the opposite operation minus plus. That's what I did. So I got two answers, 4 minus root 3, 4 plus root 3 as a 2.267 and 5.732. Which one do you think is extraneous solution? This one doesn't work. Why? 5.732. Do you see that when I plug in here, that will make it negative in right hand side. However, left hand side is a positive. So this answer do not work. So only answer will work is a 2.267. And this number is going to be my critical point. So 4 minus root 3 is a critical point. And then this becomes a local minimum. How do I know that this is a local minimum? Well, so I know that critical point here is going to, what makes it 0 is a 2.267, right? So now check this one into my sign of the first derivative. If you plug in 2.267, do you see that that's a positive, this is a positive? And if you plug in here, do you see that that's going to be positive, this is a positive? Oh, okay, we cannot plug in 2.267 because that will make it equal to 0. So I'm plugging in 2, If I plug in 2 to my first derivative function, then there's a positive, positive, that's going to be positive, positive. So 4 minus 2 is what? That is still positive, minus 1 then makes negative. So do you see that here is going to be negative? And if you plug in 3 here, then that is going to be also, no. If you plug in 3 here, then it will be positive. that will turn out to be positive. Then when you see that that's a decreasing, increasing, so it indicates as a local minimum. So local minimum is a 4 minus root 3, and then you plug in that number carefully, then you will get your local minimum of the y value. Okay, so keep thinking. Okay, class, let's look at with my decimal answer. So I want you to punch in this function into decimal and see that your minimum matches with your value. I got 26768, and then I got 1.533. I tried to explain how do I know this one is going to be negative positive. Earlier I explained a little bit wrong. So what you need to do is you have to plug in 2. Now if you plug in 2, then this side will be negative number. I'm not going to plug in, I want you to plug in. And for me, I know that why I plugged in for you. I plugged in and checked. And then now if you plug in 3, then actually there will be positive in this side. So you have to plug in with your calculator, then you get negative and positive. Therefore, you can see that this is going to be decreasing and increasing. So confirm that this is local minimum. Okay, there's one more of in-class activities, and then I want you to try that, and that's it for today. Okay, class, let's look at the answer of the last one. How did it go? If you don't understand, try to understand the next section again. So when you take the first derivative, I got this one. After I organized, in order to find critical point, I set equal to 0. So I found my x value as cube root of 10 over pi. You see that cube roots do not have a plus minus, only positive. So I found critical value. Then, now look at, we need to find out or prove that is this maximum or minimum. I know that it will be either max or minimum since it's a 0. So I'm going to plug in number. I plug in this one into calculator, turn out to be 1.471. Class, when you do this one, how do you know that your answer is correct? Punch into decimals and then check that value is the same. Like look at mine, punch into the decimals. See the number 1.471. If it's the same in the decimal, that means your answer is correct. So check that with the decimals. And then come back here. And what I did from the equation, I plugged in smaller than 1.471. So I plug in 1 here. So when I plug in 1, you see if you can do mentally with me. If I plug in 1, I have a 4 pi minus 40 over 1. That will be definitely negative value. Do you feel that? And so I got negative. Of course, you can punch into calculator. And then next one, I plug in 2. So plug in 2 here. That's going to be 8 pi minus. If you plug in 2, that's going to be 10. But 8 pi is going to be 3.14 times 8. So that will be positive, right? So my first derivative graph shows a negative to positive. That means decreasing and increasing. So what does the 1.471 indicate as? That has to be local minimum. So that's local minimum. I plug in that value to original function. Then I got about 40.788. That's how I got my values. So that's it for 4.2, and then next one we are going to do word problems. So we will use exactly same calculation there. So I want to keep playing with me, and I will see you at 4.3 on optimization of the word problems. Good job, everybody.